homework is going around. The solutions to the exam were posted this morning. I still haven't figured out how to send you guys an email. I posted the new homework over the weekend, but didn't note that. I tried to send you guys an email actually in the middle of last week, and Blackboard was set up such that I spammed last year's class twice, actually 3 times. But anyway, so the homework's up, solutions are up. I don't have the homework-free solutions up, but that will be soon. Any questions, procedural questions, anything like that? Okay, so let's start. On Friday we stopped. I had introduced the notion of the Gaussian. And we talked about it, sort of its mathematical properties, the so-called bell-shaped curve, better known as Gaussian. Sometimes it's called a normal curve, normal distribution. But now let me try to relate that to what we were doing the day that I played around with the computer. Right? If you remember that day, I was adding up waves. I added up waves that had one value of k, and then I added a wave with a slightly different value of k, shorter and longer. And I ended up creating something that looked like this. It was a packet in X. Okay? And if you remember, in K, I had the amplitudes. Let me write that out. The amplitudes I had were something like that. Remember that? Or I didn't draw lines that time. I just drew it as dots. But I had that graph in the computer. And what I literally meant is I took, let's call this height 1. I took 1 and that was k0. And if this is, say, there were 2, I took equal ones. Let's say a little bit higher than k0. I took an amplitude of, say, 0.9 of those, 0.8 of these, etc. And it wasn't an accident. I actually mathematically grabbed the amplitudes of those k values from the Gaussian probability distribution. In other words, I calculated something like that. I picked a number to be sigma. I chose k at one place 1.1 times k0, and I simply calculated this thing. It's a number a little less than 1, and I grabbed that, and then I made that the amplitude of the wave that I added in. Okay? So I had a kind of a Gaussian looking, well, it was a Gaussian packet in K, and it actually looked, the envelope of this guy in X is sort of Gaussian looking too, right? In fact, and that's no accident. So I'd like to kind of explore that. And at this point, though, I'm going to mention, and we'll use just a little bit, and I have assigned a homework from, and it's sort of advanced math concept, which you are going to get several times in your career. It's actually a sort of a fundamental feature in modern physics. And there's a number of ways to look at it and go about it. I'm only going to give you a taste. There's a lot of that in this class. I'm going to try to do anything systematically. Some things I'm just going to give you a taste. This is just a taste. Although we're going to use it a little bit, but I'm not going to prove it at all. The taste is as follows. What I did so far is I constructed psi of x. Remember, this is what I did that day in the computer. By summing over some amplitude for some particular value, k sub I of x, so some value of k with some amplitude, and I just summed these up. And remember, I showed that if I took all these things closely spaced, I ended up with a packet that was sort of isolated, another packet that was far away. And then I noticed that if I made them finer, the spacing, more and more of these, without really changing the shape of this distribution of them, I could push the packets, the next packet off to infinity. And I said I really needed to turn this into an integral. For any real system, I needed to do this. Okay? And that's fine. And so it's kind of a general notion that a wave function in x should be constructed that way. From different amounts of waves that have a fixed value of k. Now, the mathematical theorem that I mentioned is called the Fourier Transform. And it's pretty remarkable. It says that if you have this formula, which I know is a kind of, oh, I'm sorry, and I'm integrating from minus infinity to infinity. I know this is kind of new to you and kind of a little bit weird. Psi of x is made of things like this wave, this complex version of writing a wave, a sine or a cosine, this is of course cosine plus I sine, times this weighting factor in k. The Fourier transform, or the Fourier transform theory, says that A of k, remarkably, if I know this, and I didn't have this yet, well, let's suppose I knew that I did something like that, but I didn't know the values over here. I just give you this waveform. In other words, if I showed you this result of creating this packet, then in fact I can find out what A of k was like this. It's almost the exact same integral. Okay? This is called the Fourier transform. This is called the inverse Fourier transform. Doesn't really much matter which one is the transform and which is the inverse. In fact, I always forget. Then I have to go look it up if I care, which I don't usually care. They're remarkably similar. Notice that ikx in one is replaced by minus ikx in the other. And this coefficient out front is replaced by 1 over 2 pi times the coefficient out front in the other. And that's it. There's this neat thing that the function in space, x, built up of different amplitudes of k. And remember, k is momentum. Although if we're just talking math, k is just anything. This way, then A of k can be found by doing this integral, which is the exact same integral as that integral, but with I going to minus I. Okay, and here I integrated over k. Notice this is an integral over k, and I've got k within this integral and x. I don't integrate over x, I get a function of x. Here I integrate over x, and I've got a lot of x's in this thing, and a k, but I don't integrate over k, I get a function of k. All right? And let's think about the physics behind this. This made me seem a little abstract and dry, but what it's saying is if you give me a pulse like this, I can find A of k. And just like we had that the probability of x, I'll drop time for a second, is psi star of x times psi of x. And pretty soon, probably Wednesday, we're going to calculate some examples of actually finding the probability. So this is the probability the particle is at x, and I find it from my wave by essentially squaring the wave, or complex conjugate times the wave if it's if it's complex. Okay. Similarly, the probability of k, and remember that momentum is h bar k. So this is really the probability of momentum is A star of k times A of k. Okay, in the same way. So if I have this packet and I find A through this mathematical bit, then I can find the probability that it has any momentum. In the thing I built up, I showed you A of k because I used it to construct the packet. And this is the probability that the momentum had any particular value. Okay? And it was a Gaussian, it has a width, and there's an uncertainty. And that's how it all fits together. Now, if you believe that Fourier transform theory, I can prove, or nearly prove, I nearly prove the Heisenberg uncertainty principle for momentum in x from it. Let me do that. Let's choose, and this is in the book, I'm going to choose a packet, psi of x, to be basically e to the I k0x. So there's sort of one value of k in there, multiplied by a Gaussian, e to the minus x squared over 2 sigma x squared. All right, so that's something where there's an intrinsic wave of k0. And of course, a wavelength is 2 pi over k0. All right? Right, so this is basically, mathematically, I'm just taking e to the I k0x, which is a wave, and I either plot the cosine or the sine part of that. And then I'm multiplying it by the amplitude, this term. And so that just shrinks it down. This thing goes to 0. This thing goes to 0 when x gets big. And near the origin, at 0, it's 1. And so you're just left behind with the wave, right? So I hope you all can see mathematically why that is just the type of pulse we've been talking about. Everyone happy with that? Okay? So now, my Fourier transform theory says, fine, I've got a wave function, this is its form, it's kind of the simplest possible packet wave function I can imagine. By the way, I have to have this exponential, this wave part. Otherwise, I guarantee you, it's got nothing to do with anything we found in quantum mechanics. I mean, I could write down psi of x anything here, right? I mean, I could have just written down an exponential, a Gaussian alone, just this term. But that's not going to be a wave, and it won't be the solution to any real problem. It won't be the solution to any sort of standard problem you might run into. But this would be a decent representation just of an electron, or sort of anything, actually. Okay? So, let's find A of k. It's 1 over 2 pi. I write down psi of x, e, and there's some constant here, which I'm going to not really worry about. E to the minus x squared over 2 sigma x squared. E to the I k0x. And then that was psi, and then I have e to the minus I, oops, I forgot x, k0, kx. And I'm integrating over x. Okay? Look, this is just a bunch of terms, e to the something, e to the something, e to the something. That's just e and a bunch of terms. There's minus 1 over 2 sigma squared times x. And then there's plus I times k k0 minus k times x, right? That's just this thing, dx. That looks ugly. You've never done an integral like that, I assume, right? And I'm integrating from minus infinity to infinity. Yeah?
Did you take the x out of both times?
No, I meant to square that. Sorry. So, very straightforward here to here. Now, in some math classes, you will learn how to do integrals like that. For now, you can check the front of the book. And on the inside front cover, we have FOB. Back in the 90s, that meant Friends of Bill. But now it means front of the book. Okay? The integral of e to the minus az squared plus bz dz from from minus infinity to infinity is, well, it's a constant out front, pi over the square root of a, square root of pi over a, e to the b squared over 4a. And I'm certainly not going to derive that, but it is. That's what this integral is. And let me go ahead and erase this so I can continue. It's all very straightforward, just a little bit of algebra. So a of k, let me see, it's going to be pi, I'm going to have to plug in pi over a. Clearly here, a is minus, no, there was a minus sign in the definition of a, so that's just 1 over 2 sigma squared. Okay, and I'm forgetting to, I have a little x subscript, which let me keep. I also have, and let me erase this line. I also have b is just I k0 minus k. Okay? So I have, this is the integral. I had c over 2 pi. Now I got that. Actually, I don't care about the constants. Let me just write it as some new constant c prime, which will be c over 2 pi times root pi over a. But I don't care about that. Then I just have to do exponent of b squared over 4a. Exponent b squared is I squared, k0 minus k squared, divide by 4, divide by a, but a was 1 over 2 sigma x squared, so that's 2 here, sigma x squared. Still some constant. I squared is just minus 1. K0 minus k squared, I'm just going to rewrite that as k minus k0 squared. It doesn't matter since I'm squaring it, I can just reverse it. You know, basically I'm multiplying by minus 1, but then I'm squaring that. So that's the same. 4 there, 2 there, that's just a 2. And look at this. Basically, I'm supposed to write 1 over sigma x squared here. Okay? But look, that's a Gaussian. That's a Gaussian with sigma p squared. If I just say sigma p squared equals 1 over sigma x squared. Or more strictly, I shouldn't say p, I should say k. I'm sorry, sigma k. That's just a Gaussian again. Okay? So, if I choose psi of x to be this nasty thing, which graphs like that, which is the simplest possible way I can think about writing down something which is a wave somehow, that's the e to the ik0x part, but is still something like my original notion of a particle, which is the envelope, which is the Gaussian envelope, a of k, by God, is indeed just like I was showing you with the explicit math earlier. Okay? And it's Gaussian, it's centered on k0, and it has a width, sigma sub k, which is equal to 1 over sigma sub x. So whatever width I chose for this Gaussian envelope here, where that was sigma sub x, right? I get 1 over that as the width in K. So a Gaussian wave packet is Gaussian in both X and K. And just one last word on that. If this is true, then sigma K squared sigma X squared is 1. We're taking the square root. Sigma K sigma X is still 1. Okay, for this situation. Let me multiply by h bar. And, you know, I know that h bar k is p. And if sigma means sort of a, you know, delta in k, if sigma k is sort of like a width in k, if I multiply h bar times sigma k, I'm just multiplying h bar times the k, so that's nothing more than delta p, or sigma p. Okay, so h bar times the width in k, written as sigma, is no more than sigma in p, i.e. sigma p times sigma x is equal to 1. That is equal to h bar. Or I can write that as delta p. Again, people just like to say delta x, delta p when they write down the Heisenberg uncertainty principle, but typically the definitions are a little loose, but typically what you mean is the sigma. And remember how I defined sigma. Here it was just this constant in the Gaussian, but I told you it's the same as the standard deviation. If I use this probability distribution to calculate the difference between the thing and the average thing, square that, take the average, take the square root of the whole shebang, that's what I mean, okay? So it's just this measure of the width. And basically that was essentially the Heisenberg. I come back with the Heisenberg uncertainty relationship. Now the Heisenberg uncertainty principle said that it has to be bigger, the product of the two uncertainties has to be bigger than h bar over 2. Here I got h bar. So I didn't meet the minimum. I could have picked a situation where the product was a little bit smaller, but this actually isn't bad in terms of having a small value for the product here. Okay? But so this is a very concrete example. It's a little bit mathematical, and this is as much as I want to talk about this. I gave you a couple of homework problems where you are supposed to calculate a Fourier transform. Okay? In one of them I ask you, the book asks, what momentum are allowed or not allowed if I gave you the psi of x, and then you calculate the Fourier transform. And the answer comes from recognizing that the probability of k, which I'll turn into the probability of p by just multiplying k by h bar k, okay, comes from a of k squared, or, well, a of k times a of k star times a of k, right? And that's the probability that I get a momentum. So if I have, so this is what my a of k looks like in this case. What's the most likely momentum? K0. Okay. Could I get a value of k equal to like 100 times k0? That would be way out here. And the answer is no. The probability a of k is shrunk to 0 there. If I had an a of k, which did, and this is actually fairly common, if I had an a of k that did something like this, that value would be very allowed. This value would be not allowed at all. And that's what your homework is going to be like. Just you can't have that value of momentum. Okay? Okay, so I'm going to stop here. I know this is a bit mathematical, a bit abstract, but this is how the things work. And this Fourier theorem, you're going to be using over and over again. Fourier transforms, Fourier series is another version of it. Okay? I'm sorry, before I stop, I want to say one last thing about a Fourier transform. Let me just write the Fourier transform down one more time and just say something about it. When I write this, psi of x is the integral of something a of k e to the ikx dk. And then it turns out a of k is just the inverse transform. All right? Those are the series, the pair of transforms. What am I saying? Just as kind of a mathematical statement. I'm saying something kind of neat here. I'm saying give me any function, anything. Well, not anything. There's just a couple rules. It only really talks about functions that don't go off to infinity. In other words, mathematically, I only want to think about functions that are essentially some sort of thing around 0. I don't want to think of the simplest, like a simple function like x squared, which goes off to infinity and off, to infinity. The function gets to infinity as x goes to infinity. But as long as I avoid that, if I have any old mathematical blob like that, which is psi of x, and we can even forget, if you'd like to for a moment, that we're talking about quantum mechanics. That's just some function. The statement is that that function can be built up from a series of waves with different wavelengths, okay? And this is the mathematical prescription to find out how much of each wavelength there was. And there's an exact I could exactly have replaced k with omega and x with t. And there's an exact analogy that any old pulse of sound can mathematically be thought up as consisting of a series of waves with different frequencies. Okay? And so you've seen this probably in music, in stereos, right? The notion of like, that people will do spectral analysis of an audio signal, and they'll say how much of which frequency was in there. That's the mathematics that lies underneath it, okay? And of course it's deeply embedded with quantum mechanics, because quantum mechanics is all about waves. And these are basic features of waves. And this is kind of a neat and profound thought. And who would have guessed that that can be built up of an infinite set of infinite waves with an amplitude of each wave chosen such that it cancels out everything out there, it cancels out everything over there, and basically any function you draw here, including the one I just drew, okay? If I can draw it, you can calculate that envelope function a of k that will reproduce this when I add the infinity of waves going from k equals minus infinity to k equals infinity. With that amplitude, I can produce this again, okay? And I can think of it as an abstract, I'll do true integrals like this on pencil and paper, or with fine enough resolution on a computer, I can just do it directly, okay? In fact, there was a big breakthrough in the 1970s when someone came up with what's called the fast Fourier transform. It was a very efficient and fast algorithm to do that, and it enabled a huge generation of huge leap in our ability to do digital information transfer, because it allowed people to break down waves that you would transmit digitally into their frequency components. And it underlies all of the compression technologies that are used for like videos you watch, okay? Or JPEG files. They actually use these notions, and they actually do calculations like this. Okay, but I've gone way off topic from quantum mechanics. So let's come back. All right. All right. So let's put a particle in a box. So this is the standard first problem in quantum mechanics. Have any of you seen this worked out before? No. Okay. Almost no one. All right. Well, the problem is rather simple. We want to describe a particle actually doing, I mean, it is about the most basic problem you could possibly think of. Although in quantum mechanics, the most basic problem you can think of is a little different than in normal mechanics. It's actually the analogy of literally a particle in standard mechanics which is sitting there at rest in a can, okay? And doesn't have enough energy to get out of the can, all right? What we'll do is we'll draw a potential as follows. Let me draw it here and leave it here while I discuss how we're going to do this. We draw a potential U of x. Oh, I'm sorry, before I draw the potential, let me remind ourselves, what we're doing is we're solving this problem, this equation. That's the Schrodinger equation. And I'm not sure I was strict before about doing this, but that's the wave function. I use this symbol, it's a capital psi, which is going to be important in a minute. I'm going to distinguish the capital psi from the lowercase psi. Yeah, did I forget a minus sign? No.
Isn't the time derivative supposed to be the second derivative rather than the first derivative?
No. That's a good question, though. Did you hear what he asked? Isn't this time derivative supposed to be a second derivative instead of a first derivative? Why did you think that?
Because you once went over an equation similar to that, and it was the second derivative.
Yeah, no, that's a very nice observation. I pulled a fast one in a way. I introduced waves by taking the standard wave equation. The standard wave equation is two time derivatives of something. I think I called it g, with the velocity squared out front. There is two space derivatives of g is equal to two time derivatives of g. And that's the standard wave equation. This is the wave equation that's used in electricity and magnetism to describe light. Having argued, oh, waves, and then we did waves, and I did razzle-dazzle with waves, then I said momentum is h bar over I d by dx, and I said energy is I h bar d by dt, okay? And then I just plugged into 1/2 mv squared equals p squared over 2m is my kinetic energy. And then this is just standard energy. And then that's just an energy equation. And the fact is that I only get one derivative, okay? So that is not a wave equation in the sense that that was a wave equation, okay? Should I get too bothered about that? Well, I'm glad you caught it. I actually kind of meant to mention it. Well, you shouldn't get too bothered. Because I have, derivatives equaling other derivatives of a function, I'm going to get solutions which have wave-like properties. They won't necessarily be the classic wave over there all the time, okay? So it's basically, if someone tried to tell you that this was the only possible wave equation, they lied a little bit. I guess that's really the story. This is also a wave equation, okay? But it is a little different. It's not two time derivatives. Okay, so how am I, okay, and so that's the Schrodinger equation. Any problem then amounts to just picking the potential. We don't talk about forces anymore. We're not going to use forces. The reason behind that is beyond the scope of this class, but we just can't. With this sort of formulation, the notion of a force is gone. It's got to be replaced by a potential. That shouldn't worry you too much. I mean, if I had a force, I always had a potential as long as it's a conservative force, okay? And at least in principle, any non-conservative force like friction, actually at some microscopic level where quantum mechanics applies, was due to electric and magnetic interactions, and those are described by potentials. Okay, so I don't lose generality to insist that I just use the potential formulation in mechanics instead of forces. So here's the potential. I want the particle to be in a location. So here's x, here's 0, here's L. I want the particle to be in there. Simplest thing is to make u equals 0 inside and to make the potential equal infinity outside. Okay? We're going to call this region 1. We're going to call this region 2. And we're going to call this region 3. It's kind of ugly, but if I want a simple problem, that's what I do. Okay? Now, I'm only going to get so far today. The first thing I'm going to do is look at this equation. Sorry, my handwriting was pretty bad there, but there it is. The first thing I want to do is the fact that it's got x and t in it. I'm going to use a trick. Remember I said this is a differential equation. This is actually what's called a partial differential equation because it mixes x and time, and these are partial derivatives of either. I'm going to use a trick that I can't always apply, but I can try it always, and if it works, as I told you, there's a theorem that you prove at the beginning of a differential equations class where you show that if you get a solution for a particular problem, then it's the only solution for that particular problem, which is really nice. So I won't worry too much. This trick seems a little bit, I mean, it seems sensible at one level, but I don't know, I'm always left with the feeling, no, you can't get away with that. And the trick is the following. Capital psi, the function of x and t, I'm going to say is a function of x and a function of time. Okay? I'm just going to suppose that. Okay? And you might say, wait, that's crazy because last week I kept talking about that as a solution to a wave equation. This does not follow that form. Does not, right? But okay, don't worry about it. This is appropriate in other problems. This is appropriate in this problem. I'm just going to assume it can be broken like that. So plug this in. I have minus h bar squared over 2m. I'm to take the x derivative of this. And of course, it doesn't affect phi. And when it's affecting psi is only a function of x. So I no longer have to write partial. I can write full derivative. And note that's my lowercase psi, and that's my capital uppercase psi. Equals, no, plus, and phi goes along for the ride, plus u psi phi. I'm not writing the of x and of t. You got to just keep them straight in your head. I h bar d by dt, again, doesn't affect psi, does affect it does affect phi. So I h bar psi d phi dt. All right? This is all pretty straightforward, but I'm going to throw a couple of curveballs, okay? Now what do? I divide everything by psi times phi. And by the way, you have to be able to do this. Okay, you're watching me on the board. You need to learn how to do this type of manipulation. So I divide everywhere by psi times phi. That's fair enough, I can do that. They cancel here. Phi cancels there. Psi cancels there. Okay? And what I end up with is minus h bar squared over 2m d squared psi dx squared 1 over psi plus u equals I h bar d phi dt times 1 over phi. Okay? Now, here I'm going to make an argument. All of this depends on x. This depends on t. On time. Okay? So I'm going to tell you what I'm going to tell you something, then I'm going to say it again because you really got to get it. If the left-hand side depends only on x, and the right-hand side depends only on time, then both sides have to equal a constant. Okay? Let me say that again and explain it a little more. If the left-hand side depends on x, and the right-hand side depends on t, and I found a function psi, and I found a function phi, and they're doing their thing, let's just pick a point in space and think about the phi part, and time varies. That's to say, I fix a point in space where I'm going to examine this overall solution. I claim I found a solution. If I pick a point in space, I'm freezing the left-hand side. And yet the right-hand side has time in it, and I can ask, well, what happened 10 seconds ago? What happens 10 seconds from now? And this side should vary. Conversely, let's take time equals 0 for this overall solution, and think about examining different places in space. U depends on x. This depends on x. There's no time dependence over here. So this thing can be varying all over the place, but this side is frozen. It must be that the two of these are equal to a constant, which we'll call C. In fact, no, I'm sorry. I'm going to call it E, because it will turn out that it's the energy. Okay? So did you get that? This is called separation of variables. It's a technique. Separation of variables. It's an important technique for solving these problems. And it did cleanly separate. If the differential equation had been different, it might not have separated, okay? And then this wouldn't have worked. If the differential equation didn't allow it. For instance, if U, the potential, mixed up space and time, if there was a time-dependent potential, which, by the way, is what? It's a time-dependent force, which is actually a non-conservative force, okay? Then I couldn't have used this technique, all right? But that's not the case here, so I could use this technique, and you can use this technique a lot. And by the way, I said something stupid. I said that that does not follow this pattern. Yes, it does. It's e to the ikx times e to the minus I omega t. So it absolutely does follow this pattern. I was just being idiotic, okay? I was extemporaneizing or whatever, and didn't work, okay? Okay. Let's look at the time equation. What is it? It's that E equals I h bar, let me write it out a little bit, equals I h bar d phi dt times 1 over phi. All right? I can rewrite this. This is I h bar d phi dt equals E times phi. Just multiplying by phi and rearranging. There's a systematic, I can guess the solution to this, but there's a systematic way to solve this. Does this equation, this type of equation look familiar to you? Yes, no? This equation pops up all the time. You should get really good at solving it. It's the derivative of something. Okay, here it's a little weird because it's phi instead of like x or something, or f, and t instead of x, but who cares? The derivative of something is proportional to the something, right? And I know you've seen this. You've seen this in early calculus in high school. The solutions are always exponentials, all right? Let's just solve it. One way to solve it is I just rearrange d phi over phi equals, and I'll rearrange a little bit, e over I h bar dt, okay? And I integrate, that's a constant. I'll integrate from 0 to some time t, and I'll integrate from some initial value of phi to whatever value of phi is at time t, okay? That integral is a logarithm, and it's the logarithm of phi, and then I evaluate it at phi minus the logarithm of phi 0. That is just to say logarithm of phi over phi 0. And the integral of dt is just t, evaluated at t and 0. So this is just E over I h bar t. Okay? And I've run out of board space, so I'm going to have to pop back over to here. Apologies. So phi over phi 0, taking the exponent of both sides, is e to the e over I h bar t. Finally rearranging. A little trick with I. If I have 1 over I multiply that by I over I. That's equal to I over I squared, which is minus 1. Right? So I can move I from the numerator to the denominator by multiplying it by minus 1. Right? So that's the solution for the phi part. Now, I'm not going to have time, we're almost out of time. I'm not going to talk about the x part. That's what we'll pick up on Monday. Let me just make a couple comments about the time part. Well, one is that whenever I see this type of construction, I can just identify E over h bar as an angular frequency, omega, just in a mathematical sense, right? I mean, I said that if I have a wave, the time part, e to the something times e to the I times something times t, that's something I'll call omega. And I thought about what I meant by period and frequency of a wave, and I concluded this is the angular frequency. This is 2 pi times the frequency of the wave, which is 2 pi times 1 over the period of the wave. This is also Einstein's postulate for the energy of or Planck's postulate for the energy of a photon. Although here, I may not be talking about a photon at all. I simply said, I'm going to solve the wave equation. I get to this point, and I just say there's a frequency associated with the wave that's related to energy in the same way. Okay? Now, what does this phi of t do? In most cases, and in this case, I'm solving the particle in a box here. I really am. What's the probability of something happening at a given time? It shouldn't be because I kept saying the probability is the wave function complex conjugate squared, okay? For the time part, I only have to examine phi. It is phi star of t times phi of t. That's just phi 0 star phi 0. In other words, the magnitude of phi 0, whatever it is. I haven't found phi 0 yet. It's squared. It's a constant, right? This star is with the plus I times this without the star, and the phases cancel. I didn't do that too fast for you, right? You understand this? I went through it several times last week. The probability is independent of time. So this is a little bit weird. I've introduced this thing, this phase, if you will. Remember, we always call this overall a phase. E to the I something, we call that the phase. The phase is sitting there oscillating. Something about the wave is oscillating. The wave, psi. We're going to find the x part. The phi part is oscillating. But if I ask, what does that oscillation do? To ask a real question about the particle that is in the box, I examine P of t, and the answer is that it's a constant. Okay, so in fact, this thing does have some importance in certain systems. You can prove that there was this quantum phase. But in most problems, and including this one, you can't see it. It goes away. It's just some energy, it's just some frequency associated with the energy by the formula which did apply for a photon, really related to real frequency to an energy. But here, it's just some phase that kind of goes along for the ride and disappears when I ask about a probability. Okay? And so the solutions, the states, are independent of time. Which is to say, when I find out what this particle is doing in the box, at least in this way I'm formulating the problem and looking at it, the particle is going to sit there for all time. It won't change. Okay, and that's a common feature of many quantum mechanical systems. And so I'll stop there.